Welcome everyone. I hope you can hear us well. But I guess so.
Yes.
Hi, hello.
Yes.
Good. I see that we are around here already in the room. That's perfect. So I'm here in the room with Jean-Marc. And we are both going to present you the latest developments of the TRAFIR project, being the analytical method that we have implemented in what we call a simple tool, because it's basically just an Excel sheet, and also the developments which allows to run traveling fire scenario with the TRAFIR. So we will have, I will start with the analytical method for around 40 minutes, something like this. Then, if you don't mind, we'll do the Q&A after the presentation. Then we'll have a short break of, let's say, 10 minutes, something like this. And then Jean-Marc will start his presentation for TRAFIR. And then same, we'll try to keep the questions for the end of Jean-Marc's presentation. So that way, if that's okay for you, please, oh, it started again the countdown. Okay, if that's okay for you, please please mute yourself during the presentation, unless you have, of course, something very important to say. That way we don't have any background noise, and then we keep the Q&A for. So, yeah, if you could just please mute yourself, that would be ideal. Just making sure that everybody mutes. Yeah, sounds good. So a quick reminder about the project. I think I've showed you this slide more than 10 times, but still it's still good to remind that, okay, this project started in 2017 and ended at the end of last year. So it's actually almost 1 year ago. And the context obviously is traveling fires. These fires that do not burn uniformly throughout the enclosure, but that they tend to travel and lead to non-uniform temperatures across the compartments, and so to a transient heating of the structure. They are at the moment not considered in the Eurocodes, and the existing analytical models are neglecting some parts of some physical aspects. And really the main limit in this was that the lack of large-scale test results. So in the frame of TRAFIR, we try to investigate what are the parameters which influence the development of a traveling fire, and also to create models to characterize such fires and to provide some design guidance. So here, the different work packages that we've had, I will make a very quick summary of the very first work packages so that you remember a bit what we've done. But really this webinar today is focused on the work packages 5, 6, and 7. So the analytical procedure, the FEM software, and the design guidance. At the very beginning, we have done some analytical and numerical investigation to understand a bit better what are the influencing parameters, and also to differentiate what is a traveling fire by comparison to other fire scenario. We've made an analytical investigation based on the parameters given in Eurocode 1, and we already highlighted that it was in the offices that the traveling fire scenario was maybe more likely to occur. And then also made some very preliminary CFD simulations, but okay, I won't go into the details. Then we have launched some small-scale tests in Liège University. And the main objective of this experimental campaign was to define a fire load arrangement that was going to be used for the large-scale tests. We wanted to use a wood load arrangement that was leading to the fire load of the office building according to Eurocode 112, to have really something representative of an office building and not just a random fire load given by wood creeps, like you don't know what it is exactly. And also it was very important for us to have a propagation without manipulation. We wanted everything to progress on its own. Then also there was other fire tests performed by RISE in Sweden to analyze the thermal impact near field versus far field on steel structure. But here the fire load which was used was diesel pool fires. And also the aim was to make, let's say, several burners go together and measure the radiation from one side of the burners to see how much a flame will block the radiation from a flame which is behind it, to allow us to better prepare the method that I'm going to present today. Then finally, the large-scale test. So we have conducted 3 tests in this, let's say, steel frame structure. But so the structure remained the same, obviously, but the compartment was different in a sense that we closed more and more the walls to have less and less openings. But the fire load remained the same. It was the fire load which was developed in the small scale test, so representative of an office building. And in the two, yeah, thanks. Little mic issue. In the 2 first tests, there was a traveling fire. Then in the last test, the fire started to travel, but then in the end, flashover occurred. So we could really show the influence of the ventilation condition on the type of fire scenario. Then we've launched new CFD analysis to be able to at least try to answer that question: when is the traveling fire scenario relevant? When should we apply that fire scenario for design? Because the experimental tests are of limited number, they're not enough to cover many different configurations. So that's why we've decided to launch parametric analysis with FDS, using a model that we have calibrated by comparing the results with the ones from the large-scale test. And we have varied several parameters. The first one being the openings, small openings, medium and high opening ratio, the compartment geometry, the ceiling height, and also the fire load density. Here, these 3 values correspond to if you go into the Annex E of Eurocode 112, this one, 511 is for regular office, 250 is for what we call paperless office buildings, and 730 is for commercial areas. Then we could observe the different results, the fire spread, the flame thickness, the burning rate, the rate of heat release, and so on, and try to make conclusion out of that. So what we have done, so we have obviously put all the results of these analyses in a report, but at the very end, we have tried to classify all of these scenarios that we have launched. So for example, here you can see scenarios number 1, 2, 3. It's the same compartment geometry, the same fire load and rate of heat release. What is changing from 1 to 2 to 3 is the opening, which is increasing. So number 1 is the smallest openings, then 2 medium, and then 3 high. And we have in this classification table provided fire type plus comments. So for example, here you can see for the first scenario, we have a growing fire, then run away, and then flash over, meaning that the fire don't even travel even for a couple of meters. When we say that the fire travel, for the fire to travel, we need to have the fire front and the fire back, which are progressing. Here, actually, the fire back is not progressing. The fire front only grows until flashover occurs, but the fire does not travel at all. And so that's why you can see here binary classification, 0 is when we assess that there is no traveling fire, and 1 when we assess, okay, there is a traveling fire. But here the difference between scenario 2 and 3, for scenario 2, there is a traveling, which is actually a traveling fire, which is actually quite wide, and then flash over. While for scenario 3, the fire is more narrow, and you have a flashover, but at the very end of the compartment. So here, for example, in this column, you can see percentage of the compartment when flashover occurs. So actually, it's where the fire front arrived when the flashover occurred. So in this first scenario, the fire front reached approximately 40% of the length when the flashover occurred, while for scenario 2, it was 85, and scenario 3, 95. So we have done this table for all of the scenarios we have launched with FDS. So here, for example, you have the scenario 3, an example of a clear traveling fire. During the first minutes, the fire is growing, so the back does not move, it's only the front which is progressing. Then a pure traveling phase, because you have both the front and the back progressing. And then a little what we call runaway, when the fire very quickly reached the end of the compartment. And in that scenario, we had the rate of heat release imposed in FDS, which was equal to the rate of heat release released, which means that the fire was fuel controlled. While here you have an example of no traveling fire. Like I said, the fire is only growing until flashover occurs, but there is no traveling phase. Sometimes you have a bit of an in-between situation. The fire starts as a traveling fire, but then transitions to a fully engulfed fire. So for example, here on the left side, you can see that the fire really starts to travel a tiny bit, because, okay, some of the wood blocks here are, let's say, extinguished, but very quickly the fire spreads throughout the whole enclosure. And given that type of scenario, we have classified this as not traveling, because, okay, it only travels for 2 or 3 meters, and then in the end, all the compartment is on fire. While here, okay, you have also a fully engulfed fire, which is reached after some time, but the fire had quite some time to still travel across the compartment. Some observations here, for example, we have the same compartment with the same fire load, but changing the openings. So here on the left side, we have no traveling fire behavior, and we can see actually on this print screen that the flashover is being triggered, because you can see that the little boxes which are situated at the very end of the compartment will start to burn. While here with bigger openings, we have a real traveling fire scenario. And here again, we can assess the difference while lowering the fire loads. But okay, all of this is given in the report with a lot of details. And finally, if I can conclude this numerical part with one graph, it would be this one. Like I told you, we have classified all the scenarios are as either non-traveling or traveling, 0 being non-traveling, 1 being traveling. So that's why here you can see either 0, either 1. The little dots correspond to the simulations. They're linked here with some dashed line, but okay, it has no physical meaning. It's just to better see the different colors. We have here the bluish lines and dots, which corresponds to offices, because we have 511 megajoules per meter square. The yellowish curves, which corresponds to paperless offices with 250 megajoules per meter square, and the pink red one for commercial areas. And for a given color, for example, blue, we have dark blue and light blue. The difference is the compartment dimensions. For example, here it's 30 meters length, 15 meters wide, and 3 meters high, while the second one is bigger. And with this graph, you can see actually So you have 0 or 1 to see if it's a traveling fire or not. And here you have the opening factor. So you can see what is, okay, it's a trend, obviously, because we don't have enough simulations to create a very detailed and unique criteria to say, do you have a traveling fire or not? But at least you can understand a bit what's the trend. And you can see what would be the opening factor required to have a traveling fire. And so you can see that you tend to have a traveling fire more, I mean, it's more plausible to have a traveling fire for paperless offices, which are the yellowish curve, because it requires a lower opening factor. While for the commercial areas, so the pink curve, to have your line switching from 0 to 1, you need to reach like a very, very high opening factor. And to give you a bit of an order of magnitude, I have put here on the slide some modern buildings which are fully glazed. So they have a very high opening factor, and you can see that it usually is around 0.02, 0.25. So when you see that graph, you can think, okay, actually having a traveling fire in a commercial area maybe is not so plausible. But once again, this is not at all it's an exact rule, a unique criteria. We don't have enough simulations to really be able to generate a unique criteria. It's more to provide trends and understand a bit better what are the governing parameters. And just so you know, these simulations in these compartments, which are quite big, we were using a computation cluster, and it still took weeks, months to run. So it was very, very costly in terms of computational costs. Now I come to the analytical method. So the main assumption is that we consider a 3-steps method. First, we will evaluate what's the fire geometry and what's its position in the compartment as a function of time. Then when we know that, we evaluate what's the flame temperature in the compartment, and finally, what is the still temperature of the structural member which is in the compartment. We have to make some assumptions. Okay, here there is an incomplete sentence, which are inherent to the fact that it's a simple tool. At some point, because we were working with the analytical model and with an Excel sheet, we need to make some assumptions. So we have that the plan view of the compartment is a rectangle. The floor and the ceiling of the compartment are flat and horizontal. And the plan view is divided into several bands of equal width, parallel to the shorter or the longer side of the compartment. The fire load is supposed to be uniformly distributed within that compartment. Then you have the fire that starts within one band and that will propagate from one band to the other. The spread rate is given as an input, and it will remain constant during the fire. But the rate of heat release that you prescribe can be momentarily modified if the fire gets ventilation controlled. So you have the let's say the openings which are considered in the methodology. But I say openings because what you will define in the tool is openings and not glazing. So what you defined as openings is considered as fully open. So it's up to you as engineer to make the assumption, okay, knowing that I have that glazing ratio in my compartment, I make the assumption that X% of this glazing will be broken. And so that's what I defined in the tool. The procedure is based on the virtual solid flame principle. So when you have the fire which is traveling from one band to the other, actually the fire is modeled as a volumic rectangle. Something which is important to keep in mind is that the tool is to be applied when the traveling fire scenario is relevant. The tool will not transition automatically to flashover. So really, it can be used and it can be applied only if you think that a traveling fire is likely to occur in your compartment. So the type of results that you can get after the first step, you can get the evaluation of the fire geometry and its position. So you can see what are the burning bands. But okay, I will show you the tool afterwards. It's maybe clearer like that. You can also see the evolution of the fire load density, which evolves with time. So for example, here on this graph, you can see fire load density in the band number 14 as a function of time. Here, I guess that the fire load, which was defined as input, is 511. So during the first 8,000 seconds, that band number 14 is not burning. So actually the fire load is constant and it's the start value that you prescribe. But as soon as the band starts burning, this fire load is slowly being consumed and will reach eventually 0. Then the step 2, to evaluate the flame temperature in the compartment, there is a vertical discretization of the virtual solid flame. So it is divided in several layers. And then the Heskestad model is applied within each layer to compute the temperature of the flame, which will therefore be uniform in each layer. And then step 3, evaluation of the still temperature of a column. First, the tool will evaluate the heat fluxes, which depend on the zone in which your target lies. And also it depends if the flame touches the ceiling or not. So you can see here on the scheme several zones. Depending on the zones where you are, some models will be applied or not. But in any case, the radiative and convective heat fluxes are all computed. But for example, if you are within the flame, it's the Heskestad model which is applied. If the flame touches the ceiling and that you are at the ceiling level, it's the Hazemi model which is applied. So it really depends on the different zones. Then you compute the total heat flux received by a still member at a given height, because for sure, if you look, let's say, at the column bottom or at the column top, you will not receive the same heat flux, and that's really an innovation by comparison to the previously existing methodology, is that through this method, you will end up with a still temperature which is varying along the column height. And so in the end, you can get the evolution of the still temperature at a given height as a function of time. This method was checked against experimental data. So the large-scale test that we have conducted in the frame of the project, we have compared the results of the still temperature measured during the test with the still temperature that we get with the tool. And okay, we could see that the global profile is well captured. The still temperature are safe-sided, which is usually what we want with a simple model. For the levels at the ceiling, close to the ceiling level, we can couple the results with a zone model to capture the hot zone layer. And there is just one thing, is that we noticed that the descending branch is a bit underestimated by the tool, but that was also noticed when we were using FDS simulation. So if we could not capture it with FDS, then I doubt we can capture it with the simple tool. So it's good to have that in mind. And if you want to have more details, to see all the equations and so on about this method, I invite you to read the journal paper that we have made, which really describes all the details of the method. Now, design guidance. We have prepared a little book that you can receive if you ask us. So if you're interested, don't hesitate to send us a little email. It contains two main parts. The first one is a summary of the project, the key learnings of the CFD analysis, and also a clear description of the methodology, the tool, how to use it. And then in part B, we have done 7 realistic worked examples based on real buildings and on Eurocode 1. I insist to say that these are not validated designs. These worked examples were done to vary the inputs and assess a bit what's the difference. Okay, if we use that percentage of glazing or that fire load of that speed, we get this or this results, and all the results are commented and analyzed. And also it's really described step by step, so it's quite easy to read. So now I will make you a demo of the tool for this first example, which is a paperless office. We considered that 90% of the glazing is open, which is quite extreme, but okay, that's just an example. So we have this this building. Okay, we don't have the photos of the building here, but it's a real building in Norway. We have, let's say, simplified the geometry to have this compartment, 10 meters wide, 100 meters length. The building is 3 meters high, and the openings are almost all around the compartment and a bit, so they are 2.8 meters high, not 3 meters high. And we make the assumption that 90% of this glazing is broken. So we have actually the openings which are 2.5 meters high. And paperless office building, so it's something which is at the moment not in the current version of Eurocode 112, but which is in the version which is currently being revised, and needs to designate the type of big open space offices where people do not store a lot of paper, like you can see here on the picture. So not like my office where I have tons of papers everywhere. Here it's supposed to be something quite clear. Just so you know, if you are considering a structure, a combustible structure, so a timber structure, then obviously the fire load from the structure itself should be added to the fire load density. And also here we are taking the values, the characteristic values of Eurocode 112, while in reality you should compute the design value while applying the proper coefficients as described in Eurocode 112. But okay, here we don't do this. It's just to show the example. So I quit the PowerPoint and I take the Excel sheet to show you. Okay, so that's what it looks like. At the beginning, you have a little README tab, but okay, we skip it at the moment, and you arrive here at the tab input number 1. And if you remember, the step 1 is to calculate the geometry of the fire and its position within the compartments. So here first you have to define your compartments, and you have to give all the informations which are in the blue cells. So we had a width of 10 meters, length 100, height 3 meters. Here we can define also the width of the little bends. So here we have used 1 meter. When you use the tool, it's always good to try with different width of the bends to assess a bit the sensitivity of your model. Of course, here I have a compartment of 100 meters length. If I was using bends of 20 meters, my result would not be so good. So it's always good to try to have not too few bends, and try maybe 2 or 3 numbers to make sure that you don't have a high sensitivity on the results. Then here, design fire load density. If I click on that cell, I am directly sent to another tab, which is giving me the fire load densities from Eurocode 1. So if I want to have a theater, I click here and I directly get the value for the theater. But here, like I said, the paperless office building is not yet in the published Eurocode 1, so I will put it by hand, 250, and I click to back to inputs. And then it's the same for the heat release, rate of heat release density. Sorry, I click here. I am sent to this table if I want to take the values from Eurocode. So here it's also 250. Okay, back to inputs. Then I have the fire spread rate. Here I defined 6 millimeter per second, a certain factor which is usually taken as 0.8. Then the effective heat of combustion, once again, you are sent to the table of the Eurocode. Here we took 20 as other cellulosic materials. Then the openings, when you click here, you can define your openings. So here we said that we had 2.52 meters high because we have 90% of the glazing which is supposed to be open. And the width is here 110 meters. Back to inputs. So equivalent height of the opening is computed from the previous table. The time step, you can define a time step. Here I have this value, but let's say that I put, I don't know, 500 seconds. Here I have a little warning message saying that I should have either a value below 15 or this value. And this little message is to prevent the situation where you would have the fire that, I mean, the fire load within one band, which is fully burned without having the time to propagate to the adjacent bands. So here I put back this 151. And here you have the possibility to define the height of your fire load. So in most of the buildings, the fire load is not placed at really the ground level, but it's a bit elevated from the ground. So here we put 0.3. So because I've changed some things, I have to click here on the button to launch the calculation. And okay, I need to launch it again. So I click here. And now the calculation is in progress. So as you can see, it's not instantaneous, but it's quite quick. I think we will maybe have to wait 30 seconds to have the results. So it's really something that you can use to have a very first idea of the temperatures that you can get in your compartment, because yeah, around 30 seconds. Okay, so now I finished here this input one. I go to the tab burning, and I have either the results given in graphs or in the table here. In this very first graph, if I make this little, let's say, bar moving, it makes the time progress. And you can see which bands are burning at which time step. So you can see here as a function, I mean, as a graph, but the same information is given in the table below. So for example, if I come back at the very beginning here, so the band number 4, during the 300 first seconds, this band is not burning, and then at 453 seconds, this band is burning. And here, if we look it on the other side of the table, so during the first time step, you only have the first band which is burning, then the 2 first band, 3 first band, and so on. And it's, for example, at around 1000 seconds that the fire starts to travel, because you can see here that the first band, which was at the beginning as 1, so as burning, is now back to 0, so it has finished to burn. And here it's the same information but given in another way. You can see, for example, here band number 16, at the beginning it's not burning because the fire hasn't reached that band yet. Then it burns for a couple of seconds, and then all the fire load is consumed, and it's not burning anymore. You have the same here for the rate of heat release density, which was set, if you remember, at 250 kilowatt per meter square. In this example, the ventilation is sufficiently high so that the rate of heat release density that you have given is not modified. But if I define a compartment with very small openings, then according to the criteria which is set in the methodology, which is actually the one from Eurocode 1, we would have the rate of heat release, which would be reduced. Then same information, but for the fire load. So as you can see here at the beginning, in all the bands, we have a fire load of 250 megatropes per meter square. But as the fire progressed, this fire load is slowly getting consumed. Then on this tab, you can see the evolution of the flame length, which is also evolving with time. And here in this other tab, you can see the evolution of the burning rate and of the total power in the compartment. So here you can see that we have maximum around 17 megawatts in the compartment. Then we reach the little tab input number 2. So if you remember, the step number 2 is to compute the temperature within the flame. So through step number 1, we have assessed where is the fire, what is evolution within the compartment, and now we want to compute the temperature within the flame. So we have this discretization of the virtual solid flame. Here we decide to have layers of 10 centimeters and a time step. You once again need to define a time step, which is different from the previous one. And in Eurocode 3, they advise to have a 5-second time step. So here that's what we have taken. Once again, you need to launch the computation. Here it's a bit slower, but okay, still acceptable. So if someone has a joke to tell, maybe while we're waiting, or if someone wants to say something.
Maybe you can come back to the input 1
yes.
sheet.
But no, because otherwise
no,
it will,
okay.
yeah.
Just to mention that when it said height of the fuel, it's the base of the fuel. It's not the vertical elevation of the fuel, or how high it is, let's say. Height, are very similar in English, but
exactly.
I think the variable on the second column is more clear. It's H base, it's really the base of the fuel load.
Yeah, exactly. Okay, there is a question in the chat. Is there guidance to choose the physically right fire spread rate? That's actually a very good question, because it's something which is a bit missing in the literature. We have the fire spread rate that we measured during our large-scale tests, which was around 4 millimeters per second for the traveling fire, while when we had the transition to the flashover, obviously it was a bit quicker. But otherwise, except from that, I can send you. It's not a scientific paper, but it's a publication which was done by Paul Grimwood from the UK, who's a fireman, and in his publication he has, let's say, given some fire spread rates from his experience from the fires that he has witnessed. But otherwise, it's a bit of a lack in the literature at the moment. It's true, because okay, we could only run 3 tests. Okay, so the computation is done. So now we go to this tab, flame temperature. And you can see, as before, either in a graph, either in a table, the results. For example, here at 800 seconds, you have here the elevation, so the height, and here the temperature. So as you know, in the Escostad model, you have around 900 degrees at the flame basis, and then a bit less as you go up within the flame. And you have the same information here. Then the layer number, because we discretize the flame in different layers, the time and the temperature within the flame. Then we jump to input number 3, and that's where you will define where is your structural element in your compartment. So here we will assume that we have a steel column placed at the middle, so at mid-length and mid-width of the compartments. So here AX and AY, I will zoom a bit, So it's the position of the axis of the steel member. So because we had a compartment of 10 meters width and 100 meters length, we put here 50 and 5. Then you need to provide CX and CY, which is the rectangular envelope of the cross section. But for that, if you click here, you are automatically sent to this table where you can choose directly your steel profile. So here, let's say that I have this HEM 240, then directly I know what is my CX and CY. What you can do with this little button switch is actually changing the orientation of your profile, if it's put in a H or in a Y. So I come back to the inputs. I have now my CX and CY. Also, the section factor is automatically given when you select your steel profile within the table. The coefficient of heat transfer by convection is 35 because we are doing a natural fire analysis. Then for steel, the emissivity is 0.7. We consider that the emissivity of the fire is 1, as usual. And then once again, you need to provide the width of the strips, but along the y-axis. So now we have this, let's say, grid discretization of the floor. And finally, the last thing that you need to give is the height of the steel member. So like I said previously, if you're looking at the results at the bottom, the middle of the top part of your columns, you will have different results because you have the radiation. So you have your virtual solid flame, the column, and then the radiation is computed from your virtual solid flame to each part of we have some noise in the background, but that's okay. Okay, so recalculation is indeed once again, and it's the last one. So we wait a couple of seconds. Here it's a double computation. So it's normal that after the progress bar reaches 100%, it comes back to 0. So yeah, really here we have a compartment of 100 meters length, so quite big, and the computation takes maybe in total 3 minutes. So it's very quick. Almost there. Okay, so now we go to the tab steel, and you can see here in the graph or in the table the evolution of the heat flux and of the steel temperature at the height that you have given. So here, for example, we said we want to seek the result at 1.5 meters height. So that's where we get the results. And you can see here, okay, so if you remember, we've placed the column at the center of the compartment. So during the first seconds, this column is almost cold because the fire is far. Then the fire will eventually meet this column, and so you have a quite sharp increase in steel temperature. For a given time, you have your column which is engulfed into the fire, and then the fire is going further away from the column, and the steel is getting colder. So that's how it works. If I come back now to my presentation. Yes, so here you have the results of this example that we have just done, but for different heights of the column. Okay, the profile was a bit different, but still there's not a huge change. And you can see that you have the highest temperature here in the dark blue curve, which is close to the basis of the fire load. which is logical because, okay, if you remember Heskestat model, you have the highest temperature close to the fire basis. You can couple the results with ozone to also capture the hot zone results. That's okay. I won't go into the details, but if you're interested in knowing more, everything is described in the design guidance book that we have done. And so to conclude this part about the analytical model that we've built, it allows to, in the end, determine the heat fluxes and the still temperature of a column subjected to traveling fire for structural and pre-designed purposes. The methodology is based on the localized fire models, but generalized to the situation where the fire travels across the whole enclosure. We take into account the influence of the openings through a simple concept. So we may have a limitation of the rate of heat release density due to the ventilation. Then we can combine this virtual solid flame with the zone model if you wish to also capture the transient, the hot gas below the ceiling. This methodology allows to overcome some of the limitations from the existing analytical methods. For example, now, thanks to this model, you really have the temperature which is varying along the height of the compartment, which was not possible before. But of course, it remains based on some simple considerations because it's an analytical model, so that's somehow inevitable. Very important, the procedure is only applicable to traveling fire scenarios. It will not automatically transition to flashover, and it's therefore not appropriate to represent fully developed compartment fires. And these formulas have been experimentally verified while comparing the results of the tool with the measurement from the tests that we have launched. Some further work or open question. You remember at the beginning of the presentation, we were thinking, okay, when is the traveling fire scenario relevant? Sometimes some situations are very clear. Okay, you have a lot of openings in your compartment and the fire load is quite low. So it's fair enough to consider traveling fire, but sometimes the situation is a bit blurry. Also, when you check the CFD, sometimes you have the traveling fire, which is quickly leading to a fully engulfed fire, or you have a very wide traveling fire. In such case, is it still relevant to consider the traveling fire methodology? Isn't it better to directly consider a fully engulfed fire? That's the question that needs to be. We need to bring some engineering judgment here. And also relating to the glazing, like I told you, in the tool, we defined the openings and not the glazing. So it means that, once again, we need to make an assumption to say, okay, that percentage of my glazing will be broken, and so will be an opening in the model. Something which is important to highlight also is that with this methodology, we cannot take into account some local effects. For example, in some CFD simulations that we've launched, we can't see here very well, but okay, the opening is placed here, is quite short, and it's placed at the middle of the compartment. And what we could observe is that the fire was quite quickly going to that opening because reaching for the oxygen. Then it was somehow stagnating here, not moving very quickly, and then afterwards going very quickly towards the end of the compartment when there is no more opening. So that kind of stuff cannot be captured with the simple tool. Something also that needs to be kept in mind is that for the virtual solid flame, we have considered a volumic rectangle, which leads to conservative results. In reality, we would have something a bit closer to a truncated cone. And also the fire is progressing, as we could see in the experiments, more as an arc shape and not as a really linear progression. So that's something that could be improved in the future. And that's it. I will hand over to Jean-Marc just to quickly mention that in the frame of TRAFIR, 2 FEM softwares were covered, SAFIR and also OpenSeas. But today in the webinar, we will focus on SAFIR. Here you have all the publications and also the final report, which will be hopefully released very soon. So if you're interested, you have a lot to read. And thanks a lot. This is the end of my presentation. If you have any question, I will be happy to take them now. And then after the question, I propose a break before we move on to Jean-Marc's presentation.
Hello, good morning, everyone. Can you hear me? Can somebody acknowledge?
Yes, perfectly.
Thank you. So this is the second part of this presentation. It's what we did in our software SAFIR. In this work package of the RFCS project, 2 software were considered, but I will only discuss what we did in SAFIR. So in fact, at the beginning, we had the idea to introduce this FIRE model into SAFIR itself, as we have Hazemi and we have Locafi model. But finally, we thought it would be quite complicated. SAFIR would become a very complex software with many different parts. And also to use this application then would require to have, for the users to have a license of SAFIR. Well, so we finally decided to create a new software completely separate, which we called TRAFIR for SAFIR, and which is freely available to everybody who wants to have it. So what is this software doing? First, it computes the evolution of the traveling fire according to exactly the same model as the simple tool that has been presented by Mario. So the equations are the same. For example, the compartment is divided into bands which are burning or not, in which the rate of heat release is reduced or not. In each band, the length of the flame is computed. No, in the burning area, the length of the flame is computed. And yes, we have air control and stuff. So this was for us a good opportunity to verify the 2 software because they are completely independent. They should produce the same results. There are some marginal differences because the simple tool makes the integration in time in a discrete manner, 1 line for each time step, whereas in the TRAFIR for SAFIR, which is a Fortran compte, some equations are integrated in a continuous manner, but the differences are very, very small. And then on the base of that, the software produces a file in which the information is transformed exactly in the same way as FDS is doing. And you know, you can couple FDS with SAFIR with the new command radf. And the file which is created by TRAFIR for SAFIR has exactly the same format as the one created by FDS. So that means what is the information written at different time steps chosen by the user and in a box, the dimensions of which are defined also by the user. And in this box, in fact, you can have several boxes. You have control points, and in all these points, the software would write the gas temperature and the radiance, which sometimes we call radiant intensity, coming from different directions to the control point. And that file will then be used by SAFIR to make a thermal analysis. And for SAFIR, reading that file, SAFIR doesn't have to know, and in fact, SAFIR doesn't know if the file has been produced by FDS, by TRAFIR for SAFIR, and goes on it also producing a file in the same format. So I think it's good to have an idea of the organization of the workflow and the files which are being used. I will present this graph in which the software will be in the gray boxes and the files in the yellow boxes. So we have to create an input file which must receive the name of trafir.txt, in which we describe the compartment very much in the same way as we do for the simple tool. We can write this file with a text editor, for example, opening an existing file and changing a few parameters. That's probably the easiest way. But we can use the TRAFIR simple tool, and then I will show you how you can produce directly most of the lines of the trafir.txt file. Then you start TRAFIR for SAFIR, which is an executable which runs under window environment. TRAFIR for SAFIR is reading the trafir.txt file, will produce trafir.out file in which you have some information, basic information. And also then another txt file, which is the transfer file, the one that describes the radiance and the temperature in the control points of the box. The name is box 01, but you may have 2, 3 different boxes, and then there would be box 01, box 02, but box 03, etc. You take one of these boxes, you rename it into cfd.txt, because this is the name that SAFIR is expecting to find. You create an input file where you describe the cross-section. You know, if you run FDS for SAFIR, you have to describe the file in which the structure is defined, because SAFIR will compute the 2D temperature distribution at different points along the beams for the same section. So you need another file, which is the input file of the structural analysis. On the base of these 3 files, you start safir.exe, which will produce section.out, where you have some text and some information for your eyes to read. SAFIR will produce section.xml, which you can use with diamonds to make pictures and graphs, and also section.tem, which will be used in the subsequent mechanical analysis if you want to make structural analysis thereafter. So the TRAFIR tool, the simple tool has been shown by Marion. This is the sheet called input 1. And on that sheet, you have a button which is export to TXT. So even if you are using SAFIR thereafter, I think the simple tool is a good way to tune, let's say, your input. For example, the number of bands. Do you want to use 100 bands? Or do you want to use 50 bands and stuff? This is something you can tune quite quickly. Once you have done that, this is the button that you have to click. This box will open. This is a Windows box, but the name you have to give is really TRAFIR, because the only option is a TXT file. So if you type here trafir.txt, Windows will create a file called trafir.txt.txt. And if your file manager does not show the file type of which are known, it can create a waste of 1 day. Sometimes it happened in the past. And if you click register, then you are allowed to enter 1 line of command which describes the project. And then you click on create TXT. And this is the TXT file. You see on first the line of command which has been copied, and then 3 other comment lines that you can add. And you see the information. It's the same as the one coming from the simple tool. When I run this file, I had a problem, and the problem was that the decimal separator was a comma, and SAFIR, or the TRAFIR for SAFIR, is expecting a point as a decimal separator. So I guess most of you are smarter than I am and can change that in the tunings of their Excel sheet, or if not, you just replace the comma by a point, which is what I did. Then to this information, which describes the compartment and the TRAFIR fire, you have to give some additional lines of information. Here they are. You can recognize basically the same structure as the one which is used in the input file of FDS. We did it on purpose. For example, this command &ratf is the command of the FDS software. And the number 1 is the number of boxes in the compartment where the information will be written. So if you want to compute a complicated structure, or let's say a simple example, a 2D frame with 2 columns and 1 beam, you may surround this whole frame by 1 box, but then you will have a large file, or you can create 3 boxes, 1 surrounding 1 column, 1 surrounding the second column, and 1 surrounding the beam. This is what I will do in the example. You have to give the limits of the box in the X, Y, Z direction, and the step of the points. You may see that I made a very small box, 1 meter wide, 1 meter long, and 3 meter high, with a step of ½ meter in the vertical direction. And then you have DT-RAD-F, that's the time step, 151 seconds.
So these are the limits of the box. This time step has to be a multiple of the value chosen in the TRAFIR model. Okay. Here we choose exactly the same time step, but it could be 302 seconds, for example, for writing the information in the transfer file. And the end of the calculation must also be a multiple of dt rad f. And in FDS, this command is t underscore rad f underscore end. So we choose the same command. And you have to give the number of directions for the radiant intensities. You have the choice between two values, 46, which is a cruder representation of the situation, of course, or 130. And then you can start TRAFIR for SAFIR. And it takes around 1 second to run what Mario called the first part of the simple tool. So the fire model, where do we have the fire, which bands are burning and stuff. And TRAFIR.out is written, it's for your eyes, essentially. So you see here the input data of the compartment and the TRAFIR model. And the length has been divided into 100 bands of 1 meter. Then you have some information, how long it will take for the fire to spread from one width to the next one. It's 150 seconds. It will take 1000 seconds for bands to be fully burned. The total amount of the fuel in the compartment is 250 gigajoule. Maximum power of the fire before it enters into air control, it's 700 megawatts. It's huge, but Mario mentioned we have big openings. Then the dimensions of the box, the time step for writing the information. And here is a summary, let's say, or an abstract of the evolution of the situation, very much like one of the pages of the Excel simple tool, where you could see either 0 or 1 at different time steps. So here you have the time step. Let me check this here. Each time step, you have the amount of fuel in the compartment, which is reducing, the power of the fire, which is leveling off at 17.5 megawatt, the length of the flame, which is of interest for Luigi. And here at each step, you have an information. Vertically speaking, you have all the bands, 100 bands, and you see either horizontal bar means the band is not burning. If you see an X, you have fuel control, and in case of air control, the X would be replaced by 9, 8, 7, 6, so forth, representing the percentage of the defined rate of heat release. Here in this example, we don't have air control. And the file that is created, the transfer file, is called box01txt. So you may recognize it if you are using FDS for SAFIR. So the number of time steps with the value of the time steps. Here, the directions of the intensities. There are these are the points where the intensities are computed. We have 28 of them, 2 in one direction, multiplied by 2 in the other direction, multiplied by 7 in the vertical direction. And you have the position of these points. And here are the 130 directions for receiving the radiation. And now at every time step, you have one line for each point, and you have the temperature of the air. This is coefficient of convection, which we don't use, and you have the radiation in all the 130 directions. Here at the beginning of the fire, because we are in the center of the compartment and the fire is essentially 50 meters away, we have very little radiation. We have the 133 watts per square meter, which is the noise from the far field at 20 degrees Celsius. If we go after 2 hours, okay, here we see that the radiation is still 133. These are probably the directions which are looking on the other side of the compartment, whereas the directions which are looking toward the fire are receiving significant radiation. And you need the structure.in, and you see here that I created just a column. So my structure is just a vertical column in the center of the compartment, You see at x equal 50, y equal 5, and the position z are a little bit weird. They are chosen in such a way that the points of integration, the 2 points of integration of the beam are at 0.5, 1 meter, 1.5, etc. to compare with the simple tool. The file section.in, you see here it's quite simple. You have this make tm cd. So in fact, CD stands for CFD. So here we are not using CFD, but we are creating essentially or using the same. We are using the same TXT file, the same transfer file, and we are going to create a TEM file for each point of integration along the beam. And we give the name of the input file which describes the structure. And here on the boundary conditions, you have the fluxes, and they are called CFD by analogy because SAFIR is reading a transfer file, which is the same as if it had been produced by CFD. And here are the isotherms. After 2 hours, that's when the fire is starting to heat the column, but not very much. But these are different positions from bottom here on the right hand side of my screen. And you see this flange is a little bit hotter than that one. And you have the same effect at 1 meter elevation, but the temperature is not that high. Mario has shown that the temperature decreases as you go higher in altitude. So you see here again the same flange, which is slightly hotter, but not very much. And here you can hardly see the ends of the flanges. And here you don't see very much of an effect. And the same vertical gradient remains during the whole fire. But now we can look in time at a certain position. So I think I would take 2 meters. And this is, you can see the time here. This is after 2 hours. So we see the effect of the fire. And the fire now is on this side, okay, on this direction. And the view factors are taken into account and the shadow effect and everything, as is typical for SAFIR. And you see here, after 2 minutes later, the temperature is still hotter on the flange that we see on the lower side. And then 2 minutes later, or 2.5 minutes later, it's still hotter on the lower flange. Well, in fact, it's not lower flange because it's not a beam, it's a column, so, but it's on the lower side of our picture. And here again, but still the temperatures are increasing. And here also, still increasing. Here we have a very much uniform temperature distribution, not exactly, but we are at the top of the temperature where the solid flame is passing. On that time step, the same. And now it starts cooling down. We don't see very much a gradient in the y direction, but it will come here. You see now we are hotter on the flange that we see here above. Okay, this flange is hotter than that one because the fire has been passing and is now on the other direction, on the other side. And it's cooling and cooling, but still during cooling we see the gradient that has reversed its direction compared to the heating phase. And if we want to see the same information, but just in a slightly different way, I will plot the temperature evolution at node 16 here and node 77 here as a function of time. So I should see 2 curves, and here they are. What do I see? I have been a little bit too crude when computing in SAFIR the temperature evolution because I took 4 time steps of 30 minutes, sorry. So this is 1 hour, 1 hour and a half. And then I jumped directly to 2 hours. That was a little bit rude. Normally I should from here start decreasing the time step and I would have a curve like this. Okay, I try to be better next time. And from here, I took the time steps, I think, of, again, 2.5 seconds. And what you see is that the orange curve is about the green one during the heating phase, and it's the other way around in the cooling phase. So the gradient has been reversed. And the shape of the curve is very much the same as those that Mario has shown with the simple tool. And the level of temperature also is quite close. So what's the advantage of this of using this compared to the simple tool, well, there is no difference in the FEM evolution, right? The difference is in the capability of TRAFIR to compute a cross-section of any shape, including a concrete section, I have to say, if you want to. And if it's a steel section and it's concave, you would have the shadow effect, and you have the thermal gradient in the horizontal direction. So if it's a column and you want to compute the buckling, the thermal gradient may have an influence. And also, this tool is not limited to a column. I've been using here a column to compare with the results of the simple tool, but you can model a whole frame, a whole 3D structure, or a truss girder, whatever you want, subjected to this transfer file, that means to this traveling FEM. And with that, I think I've shown all my slides.